Hello everyone, welcome. This is paper 1 from November 2025 and this is time zone 3. Let's have a look and see what we can do. Question 1, we have a 5-mark question. Consider the following list of 10 data items. Here they are. This data has a mean of 19.5. Find the value of the mode, median, standard deviation, and the range. So we can work through these one by one. Some of them we're going to need to use a calculator, like standard deviation. Some of them we can find just by hand. All right. Starting off with the mode. Mode, remember, sounds like most common. So let's look at this data set and see which value appears most often. So here we have 19, which appears twice. Here we have 21, which appears 3 times. So our mode, the most commonly occurring value, is 21. So writing that out, just the answer for a 1-mark question. The mode is 21. Part B, we're asked to find the median. We can actually do this by hand, but since we're going to need to find the standard deviation using a calculator afterwards, just to prevent any kind of, calculation errors or anything like that, I think use the calculator to work this out and then potentially give some greater assurance. So here we are in the calculator, going to go to tables and spreadsheets. Going to set a value, can call this x, doesn't really matter. And let's input these data values, these 10 items. So 16, 19, 21, 19, 18, 12, 16, 21, 21, 32. We could do this by hand and arrange these from lowest to highest and find the middle value. It's an odd number, so it might be a little bit more complicated, but we could. But I think this might be more streamlined and efficient. I'm just going to check that these are correct. 18, 12, 16, 21, 21, 32. All right, so menu, statistics, stat calculations. Here we just have one variable. We don't even actually give us a context or anything. So we're just dealing with this one variable, not compared to anything else. Number of lists, x. Where did we put it? We put it in x. That's all we need. Let's go ahead and find our median. So here's our median, and it is just a value of 19. So let's go ahead and write that out. B median of 19. Going to part C, we're asked to find the standard deviation. So standard deviation, remember we have sample and population. By and large, AISL often uses population. I haven't seen too many, to be honest, I can't remember a situation where I've seen sample standard deviation, but I don't think there's anything in the syllabus that suggests that it couldn't eventually, at least potentially, happen. But in this case, we assume that these are all of the data values that we have. These 10 items reflect or represent our total population. So we have our standard deviation, sigma x, as 4.96488. So let's write that out. 4.96488. To 3 sig figs, we could write this as 4.96. Last one is the range. Range, remember, is max minus min. So the total distance from the lowest value to the highest. Here's our lowest value of 12, and our highest value is 32. So I guess we can write an equation. It is a 2-mark question, so just writing out the answer, I think we'd want to actually show some process. Range itself is equal to max minus min. In this case, largest value is 32, smallest value is 12. The range, the total distance, is equal to 20. And that's it. So not a bad way to start, I suppose. Question 2. The number of words that a child understands is modeled by the equation y equals -167 plus 6,264 log base 10 of x, for x is an element of positive real numbers. So what does this thing mean? This, I guess, domain. Domain restriction, just drawing a quick sketch. If this is our number line, let's say this is 0, What we mean by a positive real number is essentially any value you could put on the number line. So it could be 1, could be 1.397 off to an infinite number of decimal places. Could be pi, as long as it is greater than 0 and positive, anything we could put on the number line. X is the number of years since the child was born, and Y is the number of words the child understands. Part A, we're asked to use the model to predict the number of words that a child understands when X equals 10. So when the child, I suppose, is 10 years old. Nice question, kind of an input-output question, just using logs. I think it's okay. Let's go ahead and substitute those values and find the answer. So here's our function right here. It's relating Y, the number of words, to the age of this child. So I'm just going to write out this function, and then we'll substitute. So log base 10 of x. In this case, x is equal to 10. So let's just substitute that value in, and then we can find the output essentially. So y equals a negative 167 plus 6,264 log base 10 of, and then 10. It's kind of interesting. Log base 10 of 10 is actually just 1. But let's go and work this out on the calculator, because I'd imagine that's going to be the most common way to solve this. So negative 167 plus 6,264, and our log base right here, log base 10 of 10. And our answer is 6,097 words. So when a child is 10 years old, according to this model, they should know 6,097 words. So writing that out, y is equal to 6,097. All right. To be fluent in a language, a child must understand at least 5,000 words. Part B asks us to use the model to predict how long it takes for a child to become fluent. Give your answer correct to 4 significant figures. Okay. Let's just be mindful. I think it's maybe helpful. 4 significant figures. 2-mark question. Be, I think, kind of ashamed to lose a mark just because the accuracy is not there. Okay. So the first question was input-output. We inputted a value of 10, and then we found the output. Here we know the output is 5,000. That is to say we're going to have 5,000 words. And we're asking, how long is that going to take for a child according to this model? What is the value of x? So let's go ahead. I'm going to actually just copy paste this function because we're going to use it once again. Copy. And in this case, we know the output, but we don't know the input. So I'm actually going to skip right to, not the end, but just put our value in of 5,000. Okay. So we know 5,000, that's the number of words. How long will it take? We got an equation with one unknown. Let's go ahead and end solve this. Menu, algebra, numerical solve. 5,000, and then we can go ahead and input the rest. Here we have log base 10 of x. Ask the calculator to solve for x. And it looks like after 6.68 years, that's when a child, according to this model, will understand at least 5,000 words. Writing that out. X equals 6.68. And remember, 4 sig figs, I almost forgot myself. 6.68147 would give us 6.681. Okay. Part C, determine if the model is realistic for a child on their first birthday. Give a reason to support your decision. Okay. So again, we'll draw on this model right here. On their first birthday, that's when x would be equal to 1. So x is number of years since a child was born. X is equal to 1. Let's see what this model would predict in terms of the number of words that they should know on their first birthday. So writing this out, oops, for C, let's go ahead and substitute. See if I can just paste this once again. That'll work. And here, we can put in a value of 1. Let's go to the calculator and see what this model would suggest. Negative 167 plus 6264. Oops. Log base 10 of 1. Okay. So, according to this model, a child would know negative 167 words. So I'm actually going to write that out and then can talk about it, I guess. So negative 167 words on their first birthday doesn't make sense because it's not really possible to, well, understand negative words. And also, if we look at our domain restriction, actually it doesn't violate our domain restriction. We still have a value greater than 0. But we can't have negative words. Realistic. It is not realistic, actually. Realistic. What can we say? We can say it's not possible to child understand negative words. Not possible to understand negative number of words. Negative number of words. Now, there can be words we don't know, but I can't exactly say that I understand negative words. All right. Question 3. Abigail is planning an end-of-school celebration. She asks all her classmates to choose both a main course and an ice cream flavor. She organizes the replies from her classmates into the following table. So here's the main course, here's the the ice cream flavors that they've chosen, and then these are the individuals that have chosen both burgers and chocolate and chicken skewers, and so on. Part A, 1-mark question, find the total number of classmates who replied. We can go ahead and add all of these. I'm going to actually add the columns and then add those results because I think that's potentially going to be more efficient. So this is 36. This is 45. This is 36. And lastly, this is 21 plus 12 is 33. Adding this all together, are there any friendly numbers? I can work this out. This is equal to 150 total classmates. And you can put that into the calculator all the same. All right. Abigail performs a chi-squared test for independence at the 5% significance level to see if the main course choice is independent of the ice cream flavor choice. Part B asks us to write down the null hypothesis. All right. Null hypothesis, given as HO. Remember, this word null is actually the German word for null, 0. Essentially, it's a nice way to remember that there is 0 difference, or it's the kind of status quo. So, chi-squared test for independence, the status quo is that blank is independent of blank. This is always going to be the form for our null hypothesis. In this case, we can just look at these parameters right here. Ice cream flavor and main course are independent. So ice, we can say, actually a little more descriptive. I was going to say dessert preference, but maybe let's just keep it as ice cream flavor. Ice cream, sorry, this is a little condensed here. Ice cream flavor is independent of main course preference. You can write that. Main course preference. I hope it's okay to use short form here. All right. Part C, find the p-value of Abigail's test, and then write down the conclusion of the test in context, justify your answer. So kind of a straightforward, or at least common, chi-squared independence test. So let's go ahead in the calculator here. What we're going to do is we are going to set up a matrix. So let's go menu, matrix and vector. Let's create a matrix. In this case, we have 3 rows and 4 columns. 3 rows, 4 columns. Let's put those values in. 15, 10, 12, and so on. Lastly, 10, 21, 11, and 5. Just going to check that they're all good here. Good, 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 good. All right, let's define our matrix. So control var. I usually call it A, but you can really call it whatever you want. Making sure we're good. Let's go menu, statistics. Want to run a stat test, and in this case, we want to do a chi-squared 2A test. Let's see, here we are. Observed matrix, we've defined it as A. There we go. So the p-value is 0.09264. Let's go and write that out. P-value 0.09264. All right. Part D asks us to write down the conclusion of the test in context. Okay. So for our p-value, or when we want to, I guess, determine the results of our chi-square test, what we do is we compare the p-value to the significance level or the critical value. In this case, our p-value, 0.0, I'm going to write it to 3 sig figs, 926. Since our significance level is a percent already, I'm going to write this as a percent. I'll write this as 9.26%. Our significance level itself was 5%. Our p-value is greater than p-crit. In this case, we accept the null hypothesis, accept HO, or kind of maybe a little more proper, we would say that we fail to reject the null hypothesis. All right. So what does that mean? It means that, well, looking at our null hypothesis, ice cream flavor is independent of the main course, or to put it more in kind of statistical context, we could say that there is insufficient evidence to support the idea that ice cream flavor is related to main course preference. So I think let's write that. There is insufficient evidence. Insufficient evidence to suggest that ice cream preference is related to main course preference. All right. And I guess maybe just thinking instead of related, let's use our dependent and independent. So is dependent of main course preference. Okay, I think we are good. Question 4. The heights of pine trees in a particular forest are normally distributed with a mean of 35 meters and a standard deviation of 5.5 meters. Part A asks us to write down the probability that a randomly chosen pine tree has a height of less than 35 meters. So they've told us we're in the realm of, normal distributions. So we're dealing with these normal distribution curves like this. In this case, we have a 1-mark question, probability that a randomly chosen pine has a height less than 35 meters. I'm going to draw a quick sketch because I think these are often helpful. So here's a normal distribution. In this case, we have a mean of 35 meters. There we go. And we have a standard deviation of 5.5 meters. The probability that a tree has a height less than 35 meters would be everything on the left side right here. Normal distribution represents all of the data, all of our pine trees. And the mean, well, our normal distribution is symmetrical about the mean. It divides our bell curve in 2 equal halves. 50% on this side, 50% on this side. Probability that a tree has a height less than 35 meters, well, that's going to be 50%, because 50% of our data falls below this mean of 35. So, answer, just be 50% or 0.5. Part B. Find the probability that a randomly chosen pine tree has a height of greater than 25 meters. Okay. I'm going to draw another standard normal curve. This actually counts for process as well. I think it's good to conceptualize what's going on as well. Here's our mean of 35. Probability pine tree has a height greater than 25 meters. So 25 meters might be along this side, or it would be certainly to the left of the mean. And it would be all of the trees to the right of this value. So we know it should be greater than 50%. For this, we can go into the calculator. We're going to need to go into the calculator to work it out. Let's go menu, probability, distributions, and in this case, NormCdf. Lower bound, height greater than 25 meters. Upper bound, we can choose something that would be realistic. You could put 10,000 if you want, even though pine trees wouldn't get that tall. 100 should be fine. If you want, you can put 10,000 or something like that. Mean is 35. Standard deviation is 5.5. Just to speak a little more on this upper bound, you just want to make sure that you cover everything to the right. Everything under the standard normal curve that is to the right of this lower bound of 25. If you really wanted to be sure, you could put 10,000, but given that the standard deviation is 5.5, 100 is going to be enough. So here we go. 0.96548, or roughly 96.5% of the pine trees have a height greater than 25 meters. So I'm going to write that out. For normal distributions, the IB accepts calculator notation. So I'm going to write this out as NormCdf. Lower bound, upper bound, mean, standard deviation. And the answer is 0.965. One thing I forgot is to put 25 here for the sketch. Okay, we are good. Part C. In the forest, 8% of pine trees have a height of less than k meters. Find the value of k. Okay, so this is actually pretty typical of normal distribution questions. Often they'll start with a NormCdf, that is to say we have a cutoff point, calculate the percentage, and then they'll switch to an inverse normal, where they give us the percentage and we want to find a cutoff point. So these are fairly common types of questions, and I think good to become familiar with. I'm going to draw another normal curve here, centered about the mean of 35. And in this case, we want to find the cutoff point. 8% of the pine trees have a height less than k. So that 8% is going to be in this bottom section right here. So I'm going to draw this cutoff point of k, and then 8% are less than this value of k. So let's go back to the calculator, and we're going to need to run inverse normal. So menu, probability, inverse normal. Area, the calculator sweeps out from left to right. In this case, we can actually just write 0.08 or 8%. Mean was 35. And the standard deviation was 5.5. Okay, we're good. So 27.2721 meters. So let's go back to the document and write this out. Here we have inverse normal. Area, 8%, sweeping from left to right. Mean, and standard deviation. And once again, our answer is 27.27, or we can write this as 27.3 meters to 3 sig figs. All right, not a bad question. All right. Question 5, a 9-mark question. The following Voronoi diagram represents a map of a town. It shows the location of 4 bakeries at points M, 1010, N, 410, P, 0, -5, and Q, -10, 4. The town center is at location O with coordinates 0, 0. Olga is at the town center and wants to go to the nearest bakery. Write down the nearest bakery to Olga. That's for question A. So remember, these are the sites. This is a point within a given cell. Any point within a given cell is closest to, well, the site that cell occupies. So since Olga is within the cell occupied by P, her nearest bakery is P. 1-mark question, we'll just write P. Before going to the nearest bakery, Olga checks on her phone and finds that it is closed. Part B asks us to find which bakery or bakeries Olga should go to instead. Justify your answer. So 3-mark question. So here's Olga right here. P is closed. She can either go to Q, N, or M. Which one is nearest? It's actually a nice kind of trick, I suppose, or way to work this out. So we can draw a circle and then find out which ones would be closest. And here it looks like Q and N are actually closest. This isn't going to be enough for the IB, but it's a nice, helpful way to say, here's Olga, which is closest. Well, it looks like Q and N are, and M is going to be a little further away. IB is going to want us to calculate the distance between OQ, NO, and MO. So let's go ahead and do that. So our distance formula is given to us in the formula booklet. Looks like this. D is equal to, then we have x2 minus x1 squared plus y2 minus y1 squared. Let's do this for MO. So let's start with MO. So here's Olga. She's at 0, 0. I think it's helpful sometimes to label these. So if this is x1, this is y1. Let's call this x2, and let's call this y2. So substitute those values and we'll find the distance from MO. x2 minus x1, 10 minus 0 squared, plus y2 minus y1, 10 minus 5 squared. 10 Minus 0 is 10. 10 squared is 100. This one, if we did this in the calculator, it would work it out for us, but negative and a negative turns positive, which means we have 10 plus 5, 15. 15 squared is 225. Taking the square root of all of that, we'd be left with the square root of 325. You can just put this into the calculator and you'd get the same. So here's the distance between O and M, 325, or the square root of 325. And this is represented in, does it say? I guess units. I don't know if we have units as kilometers or meters or so. I suppose kilometers might make more sense. Okay, so we know the distance of MO. I'm actually just going to work this out on the calculator to give a decimal. It's perfectly fine to write this as a root. It's legitimate value. But if some of you are more comfortable with decimals, or it helps to put things into context, this is equal to approximately 8.03. Okay, so that's the distance between O and M. Let's do the same for N. We can use the distance formula. I kind of want to show a different way, because I think having more ways to do something is always helpful. Essentially, the distance formula is the Pythagorean theorem. So I want to actually just show you another way to work this out. So finding the distance between O and N. O was once again 0, 0. So if we draw a right angle triangle, that's another way that we can find this distance, D. So Olga's at 0, 0. What is the leg, or the length of this leg and this leg for this right angle triangle? So she's at 0, 0. 0 to 4, well, travels a distance of 4. And going from 0 all the way to 10 is, well, a distance of 10. So if we wanted to find this value of D for, let's say, ON, I think I'm going to keep with this color, ON. What do we have? We have 4 squared plus 10 squared equals D squared, essentially Pythagorean theorem. A squared plus B squared equals C squared. Working this out, we have 16 squared plus 100, whoops, not 16 squared, 16 plus 100 equals D squared. Not exactly interested in D squared, we just want D. So let's add both of these together. And what's the opposite? Not the opposite, but how can we cancel out this squared? Well, take the square root of both sides. So in the end, D is equal to the square root of 116. I want to do that really quick for this last one, right here. Drawing a right angle triangle, and then finding the distance once again. Olga's at 0, 0. That means this is negative 10. This is 4. So working this out for this last one for OQ. OQ. What could this be? This is once again 4 squared plus, watch your brackets, negative 10 times negative 10 gives us a positive. D squared, once again, 16 plus 100 equals D squared. That means D itself, after we take the square root of both sides and so, is equal to 116. All right. Gonna take, just to compare, I guess, apples to apples in a way, what is the square root of 116? We have it in both of these cases. It's equal to approximately 10.77. So to go back and answer this question, which bakery or bakeries should Olga go to instead? Well, if she wants to find the closest one, it would be N or Q. Distance from ON is 116. Distance to OQ is root 116. This is much larger at root 325. So let's go ahead and answer this. So what could we say? Olga should go to either, what can we say, Q or N. And then our justification would be that root 116 is less than root 325, or with decimals, 10.77 is less than 18.3. There we go. Moving on. Part C. Write down the equation of a line containing all the points that are of equal distance from bakery M and bakery N. Kind of a wordy question. Here's bakery M, here's bakery N. All the points that are of equal distance from bakery M and bakery N are on this line right here. This is the boundary line, and it's the perpendicular bisector of M and N. I'm going to erase some of this. So, what is the equation of this boundary line? Well, they're both at the same horizontal, or rather vertical point. It's just the horizontal that's different, or, sorry, the x values. So, vertical lines have the equation x equals, and what would it be? In this case, it's the halfway point between 4 and 10. We can work this out as saying 10 plus 4 over 2, 14 over 2 is equal to 7. That would be the halfway point right here. So x is equal to 7 would be our equation of this boundary line right here. So they're asking us for an equation. It's when x is equal to 7. I'm wondering, just a quick kind of recap, because sometimes this is challenging. Remember, if we have horizontal lines like this would be like y is equal to 6. And if we had like a vertical line like this might be x is equal to 3. So this is the idea that x is 3 and it is always equal to 3 no matter what, it doesn't change. Same as y is equal to 6, it's always equal to 6. It's this horizontal line. Here we're dealing with this vertical line. It doesn't have a slope or anything. The slope is undefined. It's just this midpoint between m and n. Halfway point between 10 and 4 is 7. There it is. All right. Part D, we're asked to find the equation of the perpendicular bisector of MP. 4-mark question. So here's M, here's P. Perpendicular bisector is this line right here, this boundary line. So I'm actually going to draw that out. So perpendicular bisector would be this line right here. I guess we can extend it in the other direction as well. So we want to find the equation of this line. I think this is actually a type of question that shows up often enough that it's helpful to have kind of in your back pocket in a sense. And the process or procedure to solve or find the perpendicular bisector between 2 points is the same exactly every single time. So knowing that there's a good chance, or at least a fairly good chance, that this might show up and that the process is always the exact same and that they always hover around 4 or 5 marks, it's not a, I think it's one of the more important ones to remember. So let's go ahead and work this out. So what is a perpendicular bisector? Well, perpendicular bisector, this line runs perpendicular, but perpendicular to what? Well, this line segment right here. So it is perpendicular to this line segment that connects M and P. And it bisects. Bi is 2, sect is cut. It cuts it in 2 equal halves. Process that we can use to find this blue line right here, this perpendicular bisector. First, find the slope of this. Use that to get the perpendicular. That allows us to find the slope of this. Then we're halfway there to getting the equation. We just need to find the y-intercept. We find the y-intercept by substituting the midpoint of this line segment into our equation of a line, and then we're good. I'll show you what that looks like. Like I said, the process is always the same. Okay, so first let's find the slope of this line MP. Slope given to us in our formula booklet, M is y2 minus y1 over x2 minus x1. Again, I think it's helpful to label these just to keep track, but that's maybe more of a personal preference. Okay, y2 minus y1. This is 10 minus 5 over x2 minus x1. 10 minus 0. You can go ahead and put this into your calculator. Be fine. Two negatives make a positive. So what do we have? We have 15 over 10. Or as a fraction, we could write this as 3 over 2, simplified. Okay, so we know what m is. We know what m is for this line. But we don't want the slope of this line, we want the slope of this line. So if m is equal to 3, 2, the question is, what is m perp? M perp equals what? Well, to find the perpendicular, we can take our fraction, switch the top and the bottom, then multiply by -1. So switching the top and the bottom, the numerator and denominator gives us 2 over 3. Used to be positive, now it's negative. And there we go. That is our slope, our negative slope for this blue line. Okay. So we're part of the way there in finding this equation of a line. Equation of a line is given to us as y equals mx plus b. We've already found m. It's negative 2 over 3. So it's negative 2 over 3x plus b. Question is, what is this value of b? What is the y-intercept? Looking at this equation here, we have three unknowns. We've got x, y, and b. But we can, or the idea is if we can find the midpoint, a point that lies on this line, the midpoint of this line segment which lies on this line, and then we'll know an x and y value. We can substitute it in, and then we can solve for b. So let's find that point on the line, that midpoint between m and p. Midpoint is given to us in the formula booklet. It's just this. So midpoint is given to us as average of the x's, x1 plus x2 over 2, and average of the y's, y2 over 2. So working this out, x1 plus x2, this is 0 plus 10 over 2, and then y1 plus y2, negative 5 plus 10 over 2. 0 plus 10 is 10. 10 divided by 2 is 5. Negative 5 plus 10 is just 5. This would be 5 over 2. So we know a point that lies on this line, and that point is 5 and 5 over 2. So I'm going to grab this, copy it, and bring it over here. Running out of space. I'm going to try to move this up, and I think I'm actually just going to erase this, if that's okay. All right, here we are. So we know a point on the line. We've got our equation of a line. It's almost done. We just need to find this value of b. We know a value of x and y. We know when x is equal to 5, y is equal to 5 over 2. That means we can reduce this equation from 3 unknowns to just 1 unknown. One equation, 1 unknown, we can then solve. So y is equal to 5 over 2 when x is equal to 5. Whoops, I think I wrote that out incorrectly. 2 over 3 when x is equal to 5 plus b. All right, last step here, almost done. Let's end solve this, and then we can find the y-intercept. Menu, algebra, numerical solve. 5 over 2, and so on. 2 over 3. 5 plus b. Solve for b. Okay, 5.83333. If we want, we can get this as a fraction. 35 over 6. Let's go back to the document. B we found was 35 over 6. That means our equation of this line, after all of that, negative 2 over 3x plus 35 over 6. Okay. Good. And that's it. Question 6. A function is defined by f of x equals 4 over x minus 3 when x is greater than or equal to negative 6 and less than or equal to 10, and x itself cannot be equal to 0. Of course, if x was equal to 0, we would be dividing by 0, and that's in a logical statement. All right, part A, we want to find f of 10. So this is, I suppose, a kind of function notation question. What does f of 10 mean? Essentially, it means that if our input is 10, that is to say, if x is equal to 10, what is the output, or what is the result? So in this case, we can just substitute for 10 wherever we see an x, and then the result is our output, the result of this function. So f of 10 equals 4 over x is equal to 10 minus 3. And I guess we could work this out. What is this? This is 2, thinking if we should work this out in the calculator. No, we can, but 4 over 10 is equal to 0.4. 0.4 minus 3. And this is going to be equal to negative 2.6. You can, of course, work this out on the calculator and you get the same answer, all the same. All right, let's go on to part B. Part B is a 3-mark question, and here we're asked to find the range of f. So just a quick review of what we're talking about when we're talking about domain and range. Domain is a set of inputs that we can feed into our function. Here they already told us x is greater than or equal to negative 6, less than or equal to 10, can't be 0. And the range is the set of outputs over this given domain. So if we were to, let's say, start here and go something like this, our range refers to the set of outputs, the y values that we can reach, whereas our domain refers to the set of inputs. So this obviously isn't this graph here, but this is just the idea. Domain corresponds to inputs, range corresponds to outputs. So I think the most straightforward way to solve this would be to graph, so let's go ahead and do that. So here's our spreadsheets, graph and spreadsheets, and let's input our function. So 4 over x minus 3. So we know our domain restriction was between negative 6 and 10, so we can have all values greater than negative 6 and less than 10 as our inputs. So let's start off with that lowest value of negative 6 and see where we are. So graph trace negative 6. When x is equal to negative 6, the y value is equal to negative 3.667, or negative 3 2/3. And what happens as, well, we move to the right? We can't move to the left, it's outside of our domain. But we can go from negative 6 all the way to 10, not including 0. So as we move to the right, we see that, well, we go further down, or our y value becomes increasingly negative. That will continue to happen as close as we get to 0. Once we reach 0, it's undefined, but we approach this like negative infinity. It actually is negative infinity. Why is that? Just really briefly, 4 divided by some super small number. How many times can you fit something infinitely small into 4? Well, an infinite number of times, because this thing is infinitely small. And then if that thing is negative, then we have positive over negative, so negative infinity, and then even more, we can add negative 3 to that. So there's no negative value we can't reach. So I'm going to go back here. Whoops. I think I lost this function. Let me see if I can Control Z and get it back. There it is. Okay. So here we go. So once again, when we have a value of -6, we're at this value of -3 2/3, and as we move to the right, we go increasingly negative. Let's try our upper bound here. Let's go graph trace, and here we'll start at that positive bound of 10. So this upper bound of 10. So here at the upper bound, we reach -2.6, that's our y value. And then as we move to the left, we can't move to the right, 10 is the largest input that we could substitute. As we move to the left, we see that our y value increases. And just like before, as we approach 0, we are going to get a very large value of y. Once again, wondering if I can get all the way down here. Yeah. Once again, the logic is some super small number can fit an infinite number of times into, well, some number that is not infinitely small, a finite value. So we can approach positive infinity. So what is our domain? What is our range? Let's go back to the document here and I'll just sketch this out and hopefully we can bring all these ideas together. So here we are. We're starting at -6. This is our domain and we go all the way up to, we try to extend this all the way up to the value of 10. So when we started at -6, we had this value. X was equal to -6 and y was equal to -3 2/3, or it was, remember, -3.666667 and so. And then after that, it kept getting smaller and smaller and smaller. So we went down, and then we could potentially go all the way to -infinity. And same when we had this value of 10. When x itself was equal to 10, right here, we had this value of -2.6. So this was that upper bound of -2.6. And when we went further to the right, further to the left, we approached positive infinity, something like this. So in terms of the range of f, what are the possible y values we can reach? We can go all the way to positive infinity, all the way to -infinity, but there's going to be this little gap between -3 2/3 and -2.6 that we won't be able to reach. So in terms of the range, what we could say is that y is less than, could be anything less than or equal to -3 2/3. If you wanted to write it out with that decimal, you certainly could. 3 sig figs, I guess, would be -3.67. So anything less than -3 2/3 we could reach. And similarly, if y is greater, y could be greater than -2.6. So just once again, summarizing, what are the values of y that we can reach when substituting any value between -6 and 10, not including 0? Well, we can start at -3 2/3 and go all the way to -infinity. So as long as y is less than or equal to -3 2/3, this is part of our range. Similarly, we start at -2.6 and go all the way to positive infinity, so y itself can be greater than -2.6. So both of these are fine. It's sometimes a little funny, I suppose, to mix fractions and decimals, so this might be potentially the most appropriate kind of response. All right, let's go into the last question here. Find f inverse of -2. So sometimes these questions are seen as kind of confusing because of the notation, but really what an inverse does, it switches inputs and outputs. Just like here for this f of 10, we substituted a value of 10 for x, that is to say 10 was our input. Inverse switches inputs and outputs. So this -2 is our output, and now we're asking what must the input have been? So if our output is -2, what must the input have been? I hope this isn't too cluttered here, but let's write that out. Output is equal to -2. Now we want to find out what the input was. So once you get familiar with the notation, not a bad 2-mark question. Inverse switches inputs and outputs. Here we asked for the input of 10. What's the output? Here, the output is equal to -2. What must the input have been? So we can end solve this. I think we can work this out using algebra, and it looks like it is. Let's see, 1. Looks like the answer is 4, but let's go and end solve this. So menu, algebra, numerical solve. -2 equals 4 over x minus 3 as calculated to solve for x. And the answer is 4. Okay. So here we have x. X is equal to 4. Okay. And we are good. Question 7. At a sports center, students choose one activity in the morning and a second different activity in the afternoon. The tree diagram shows the probability of students choosing each morning and afternoon activity. So here are the morning activities and the probability of a student selecting each, and then the afternoon activities, respectively. Part A asks us to write down the value of A. So these are mutually exclusive. You can't do both ice skating and go-karting, and the sum itself must equal to 1. So this represents what's called an exhaustive set. You need to choose one of these. If you need to choose one, we have a 100% probability that you're going to be in one of these. If we imagine that 80%, 0.5 and 0.3, 80% are ice skating and go-karting, that leaves 20% or 0.2 left for climbing. All right. Part B. Find the probability of a student choosing ice skating in the morning and climbing in the afternoon. So ice skating in the morning, climbing in the afternoon. So if we want to find the probability of this particular event using a tree diagram, we just multiply along the branches. So ice skating in the morning, climbing in the afternoon, we could represent as 0.5 times 0.3. And that would equal 0.15. Essentially, half of 0.3 is 0.15. All right, writing that out. Since it's a find, we'd want to show process as well. So just be careful. Instead of writing just 0.15, show process. Part C. Find an expression in terms of B for the probability of a student choosing go-karting in the morning and ice skating in the afternoon. All right. So go-karting in the morning, ice skating in the afternoon. Same idea, we'll multiply along the branches, but in this case, we're not multiplying two numbers, we're multiplying a number and a variable. So same idea, but we just want to write an expression in terms of B. So not just a plain number, but number multiplied by B. 0.3 times B, essentially we have 0.3 or 30% of a B. And that would be an expression in terms of B. In this case for go-karting and ice skating. All right, so writing that out, 0.3 B. Part D. At the end of the day, 87.5% of the students choose ice skating. Calculate the value of B and C. Okay. Nice kind of question. So 87% of the students choose ice skating. So we have some value. They give us some kind of hint, asking us to form an expression. And essentially what we want to do is we want to add up the total number of events that correspond to someone taking ice skating. And we know that all of that in the end should equal 87.5%. So I'm going to, actually I'll use this space here and we can write it out. So the probability that a student chooses ice skating. So first off, what are the ways in which someone can choose ice skating? Well, we have 50%. Oops, I'm going to make that a little nicer. We have 50% choosing ice skating here, irregardless of whether they do go-karting or climbing afterwards. So we already know that we have 50% choosing ice skating, just already in the morning. They need to choose, or students need to choose, a different activity in the afternoon. So who else can do ice skating? Well, these students can do ice skating, the ones that choose go-karting and then ice skating. That would be this 0.3b students, so 0.3 times b, multiplying along the channels or branches. 0.3 times b, or 0.3, I'll write it out as actually 0.3 times b. Plus, what's the other way someone can do ice skating? Well, if they go climbing and then ice skating. And that would correspond to 0.2 times 0.625. Let's keep it at that for now. 0.2 times 0.625. So, once again, 50% choose ice skating right off the bat. There are these students that choose ice skating and these students that choose ice skating, and altogether, this should equal 87.5%, or 0.875. Just making sure that number is correct. Yeah. Okay, and I think we're good. With that, we can find B. So after that, of course, we can find C. So let's go ahead and end solve this, and then we should be good. All right. Menu probability. Probability? No, sorry. We're in probability, but we're looking for numerical solve. 0.5 plus 0.3 times b plus 0.2 times 0.625. All of this is equal to 0.875. And we want to ask the calculator to solve for b. 50%, this is good, and this is good. All right, so 0.833333. That's a value of b. Going back to the document here, b equals 0.833. So the value of b, 0.833. And these are binary events, so there's only two possible outcomes. We can imagine 83.3% of students choose ice skating, and the rest would choose climbing. So working this out for C, what's left over after we take 0.833 away from 1, this would give us, what would it give us? Give us 0.167. Okay, and that is, that's that. So let's go on. Question 8. Eduardo takes a photograph of a water fountain. He notices the path of the water looks like a parabola, and he decides to model the curve using the equation y equals ax squared plus bx plus c. Eduardo takes measurements from the photograph. He finds the distance between the x-intercepts r and s to be 3 centimeters and the maximum height of the water to be 13 centimeters above the fountain. These measurements are shown on the following diagram, where the point 0, 0 is indicated as O and the vertex T is on the x-axis. So here we have, I guess, what can we say? The diagram. Okay. First question, write down the value of C. Okay. So general form of a quadratic is in the form of y equals ax squared plus bx plus c. What is special about this c is, well, it's the only thing that isn't attached to an x, or isn't multiplied by an x. So what happens when x is equal to 0? Well, we're just left with this c. in this case, what happens when x is equal to 0? Well, y is equal to 13. That's our vertex. So, just to kind of show, I guess, what would happen when y is equal to 13 and x is equal to 0, that leaves us with c equal to 13. All right. Part 1 of B, write down the coordinates of S. Okay. Kind of nice question, I guess. So they told us that, well, they told us that the distance from the water fountain, I guess the nozzle, to the point of impact here, the distance is 3 centimeters. The vertex is on our axis of symmetry. So this axis of symmetry right here divides our parabola in 2 equal halves. So if this is 3, then this right here is equal to 1.5, as is this. So if this is x equals 0, 0 at the origin, here we're still horizontal with the ground, but in this case we have moved to the right 1.5 units. So the coordinate of S is 0, 1.5. All right. Use the coordinates of S to write down an equation in terms of only A and B. Okay. So once again, shall write it out. I think we have some space maybe here. Once again, general form of a quadratic is ax squared plus bx plus c. We found out that c is equal to 13, so let's add that in. Now here, whoops, I'm sorry, I made a mistake actually in part one of B. I switched up the coordinates. So looking at this, we have x moved to the right 1.5 units and y is still 0. So let me just correct that. So x, distance we move horizontally, 1.5. And y itself is 0. We haven't moved up or down at all. Okay. Once again, general form of a quadratic. We found c to be 13. Substitute. Now let's use the coordinates of S to write down an equation in terms of only A and B. So let's go ahead and do that. Can erase this. And that's our real coordinate. Okay. So when x is equal to 1.5, y is equal to 0. Let's substitute those values here. When x is equal to 1.5, y is equal to 0. Substituted y is equal to 0, x equals 1.5, and now we're good. Let's expand. This would be 2.25 times a, or 2.25a, plus b times 1.5 is just 1.5b, and then plus 13. I think the IB would accept this because it is in equivalent form. Let me actually look at the mark scheme here. Let's see. They will accept this 1.5 squared. So all of that is okay. All right. If we want to expand it, of course, it looks like this. Part C, we are asked to find the value of A and the value of B in Eduardo's model. Okay. 3-mark question, not bad. How can we work this out? What can we do? So oftentimes IB questions are not discrete and they're not, let's say, siloed or like compartmentalized, as in part A is part A, part B is part B. What I mean is that they often lead into one another. So we've just been asked to find an equation in terms of A and B. Approaching C, if you're unsure of the process, why would they have asked us to write an equation in terms of a and b? Well, potentially, and it's actually the case, is that we can use a system of equations to solve for a and b. So we use this value of 1.50, substitute it to write a linear equation. Using that same process, in this case, this other point of negative 1.5 and 0, we can get another equation in terms of a and b, and then use system of linear equations to solve. So let's go ahead and substitute. Here's another value of x and a value of y. I'm going to take this right here. Whoops. X and y. There we go. Here's our quadratic. Let's put those other values for x and y. Y is equal to 0. When x is equal to negative 1.5 plus 13, I'm going to expand. Negative 1.5 times negative 1.5 gives us positive 2.25 multiplied by a. And then b times negative 1.5 actually gives us negative 1.5b. And this is plus 13. So what we now have is equation number 1 and equation number 2. Two equations with two unknowns. We should be able to use system of linear equations to solve. So let's go to the calculator and work that out. Menu, algebra, solve system of linear equations, two equations. We have them written in A and B. All right. Let's write them out. 2.25a plus 1.5b plus 13. And the second one was 0 equals 2.25a minus 1.5b plus 13. All right, everything looks good. And here are the values for a and b. A is equal to negative 5.7778 and b is equal to 0. So going back to the document and writing that out, a is equal to negative 5.78 to 3 sig figs, and b is equal to 0. Okay, let's go on. Actually, sorry, I can certainly go on. One thing that's nice, I suppose, in terms of like reassuring, negative value means our parabola opens downwards, which we can confirm. So it matches what we would expect here, and it's centered about this line, about the y-axis. In that case, we would have no b value. It's just a negative value opens downwards and a c value shifted up 13 units. So this looks good. Question 9. Consider the function f of x equals x cubed minus 2x squared plus 5x minus 7. Part A asks us to find f of 1. So this is a function notation question once again. Here our input is 1 and we're asked to find the output. So let's go ahead and work that out. So f of 1, essentially wherever we see x, we replace it with 1. Input of 1, what's the output? So 1 cubed minus 2 times 1 squared plus 5 times 1 minus 7. We can go into the calculator and work this out, but I'm going to work it here as well. 1 minus 2 plus 5 minus 7. And in this case, what do we have? We have 6 minus 9, or negative 3. Okay. Let's go on to part B. Part B, we're asked to find f prime of x, or essentially the derivative of this f of x. So let's actually write out the function first. F of x is equal to x cubed minus 2x squared plus 5x minus 7. Remember in our formula booklet, if f of x, for example, is x raised to the power of n, the derivative, how do we find the derivative? Take that exponent, multiply it out in front, becomes nx, and then of course it is reduced by 1. So let's do that and work through this term by term. Okay. So here's our exponent of 3, multiplied out in front. Now we're finding f prime of x. That would equal to 3x, x used to be cubed, take away 1, now it's squared, minus, same thing, take this squared, multiply out in front, negative 2 times 2 is negative 4, x to the power of 1. You can write that, but usually we don't put a power of 1. Here, when we have just a linear term, or just an x, the variable just falls away. So we have just 5, and then our constant as well. Our constant actually just shifts a function up or down. It doesn't affect the slope, so it also just goes away. So there's our derivative right there. All right, part C. Find the equation of the line that is tangent to the curve y equals f of x at x is equal to 1. 2-mark question. I would expect this to kind of be 3 marks, but that's fine, I suppose. So just to give a kind of background, or some kind of explanation of what's going on here. We're given this kind of cubic function, and I'll draw a rough sketch of what this might look like. So there's our cubic function, y and x. And here we want to find the equation of the tangent to the curve y equals f of x at x equals 1. So if we imagine, for example, that this is where x is equal to 1, we want to find the equation of the tangent line. So remember, a tangent line just touches a line at one and only one point, and it tells us the slope at that given point. So this right here is our tangent line. Just like for a circle, I hope this isn't too lengthy of an explanation, a circle has a tangent which just touches, in theory actually, just at one and only one point. So this tangent line, here's our function. At this point where x is equal to 1, it just touches this function and it has the same slope at that point. Okay, so it's a line. It's going to have the equation y equals mx plus b. What is a slope? Well, for that we can use the derivative, and let's input a value of 1 into our derivative. Derivative gives us the slope at a point, the slope of our function at a given point. So let's substitute a value of 1 in for our derivative. So let's put in a value of 1. Let's find f prime of 1. 3, 1 squared minus 4 times 1 plus 5. Working that out, 3 minus 4 plus 5, this is going to equal 4. So for our equation of a line, the slope itself is equal to 4. Now what is the y-intercept? So in this case, looking at our equation of a line, we have 3 unknowns, x, y, and b. If we knew a point right on this function, at this given point, I suppose, when x is equal to 1, what is the corresponding y value? Do we have a coordinate point on this line? We do, actually. When x is equal to 1, y is equal to negative 3. Of course, this isn't entirely correct for this. I guess we could do this, make it correct, I suppose. When x is equal to 1, y is equal to negative 3. So we have a point on this line. And in that case, we should be able to substitute those x and y values and then find that missing unknown. So let me just move this over here. When x is equal to 1, y is equal to negative 3. And now we've gone from 3 unknowns to 1 unknown. Having a point on the line means that it satisfies the equation, so it balances. And now what is the b value? That must be the case in order for this equation to balance. Doing a little algebra, b itself is equal to -7. So b is equal to -7, and substituting here, that would be the equation of the tangent line, 4x minus 7. All right. Question 10. In a job assessment, there are 15 multiple choice questions, each with 5 answers. Only one answer is correct for each question. Adil completes the assessment by randomly choosing every answer. All answers are equally likely to be chosen. Each of Adil's choices are independent. Part A asks us to write down the expected number of correct answers. Okay, so let's start off. Expected value is given in our formula booklet, and it's given as n times p. So number of trials times probability of occurrence, or in this case, probability that we get a successful answer. In this case, there are 15 multiple choice questions, and each with 5 answers. So 15 questions, 1 out of 5, that's the probability that any of these may be answered correctly. So on 15 questions, we would expect overall 1/5 of them to be correct. You can work that on the calculator, but 15 times 1/5 just gives us a value of 15 over 5, or 3. That's our expected value in this case. Part B, find the probability that Adil correctly answers exactly 3 questions. Okay. So here they don't exactly state it, but we can use some information to kind of, I guess, narrow down the context of this question. So here we have a set number of trials. We have probability of answering correct or incorrectly. We're told that each of the choices are independent, and that is enough for us to tell that we're dealing with a binomial distribution. So set number of trials, we have this binomial, or rather binary event. It can either be correct or incorrect. And then we have independent events. So answering one event does not influence, answering one question does not influence the likelihood of answering another one incorrectly or correctly. Okay, so let's go ahead and write this out. So what do we need for a binomial distribution? We need the number of trials. We need the probability of success. And we need the number of successes. Number of successes. And if we have all of this, then we can find the probability of occurrence. So, probability that Adil will correctly answer exactly 3 questions. He's answering 15 questions. The probability of answering any of these correctly is 1 over 5, or 20%. And the number of successes we're looking for in this case is 3. So let's go into the calculator. We'll use binomial, in this case binomial PDF, and we can solve. Menu, probability, distributions, and here we want to go to binomial PDF, just an exact value. 15 trials, probability of success is 0.2, and in this case we're looking for exactly 3 successes. Probability of getting exactly 3 successes is 0.250139, roughly 25%. Let's go back and write this out. The IB allows for calculator notation for binomial and normal distributions. So let's go ahead and just write it out. Binomial PDF, number of trials, probability of occurrence, number of successes, and the answer is 0.250 to 3 sig figs. All right. If Adil answers 7 or more questions correctly, he will be offered a job. Part C asks us to find the probability that Adil is offered a job. All right. So in this case, we can use the same structure, but just modifying it somewhat. So let's go ahead, copy paste, and we will solve part C. Oops. So in this case, we still have 15 trials, 15 questions being answered. Probability is still 1 out of 5, or 20%. In this case, number of successes, he needs to answer 7 or more questions. So he needs to get between 7 and 15 questions correctly. So for this, we're still in binomial distribution, but since we're dealing with a range, we'll use binomial CDF. Going back to the calculator here, menu, probability, distributions. Here we want to go binomial CDF. Number of trials is 15. Probability of success, 20%. 7 or more questions correctly, so 7 to 15. Here the answer is 0.018059, or roughly 1.81%. So hopefully, well, okay. All right, let's go ahead and write that out. Binom CDF. 15 trials, probability of success of 0.2, lower bound, upper bound, and then our answer. 0.01805, or to 3 sig figs. Sorry, 0.01805 to 3 sig figs. 0.0181. So just about a 1% chance that that occurs. Question 11. A cylindrical shaped cake has diameter 22 centimeters and height 10 centimeters. Coco cuts the cake into 16 pieces of equal size as shown in the diagram. Part A asks us to find the volume of one piece of cake. Okay. Kind of a nice question, actually. Let's look this out. I'm going to kind of draw a top view of this cake as well. So here's the top view. Here's our center, if I can. Here's our center, and then let's draw one slice. So she cuts it into 16 pieces of equal size. So if we want to find the volume, since we're dealing with a prism, that means a shape with uniform cross-section, we can find area of the base and then multiply by its extension or its height. I just want to kind of elaborate that just a little. So imagine here, actually I'll draw it this way. Imagine here we have a piece of bread. So I'm going to draw this if I can. Just a rough sketch of a piece of bread, or a loaf of bread, I mean. So here we have a loaf of bread, and it's in the shape of a prism. What does that mean? Is that I can take a slice out of this piece of bread, and it will be uniform. It's always going to be in the shape of that, that single slice of toast bread. So uniform cross-section means that I can take a slice, so long as it's perpendicular, so perpendicular to the base here, and it will be uniform. It's always going to be the shape of this square. And when we have a prism, something with uniform cross-section, we can find the area of one of these faces and then multiply by the extension. And we can use that same principle here. If we find the area of this top portion, or the area of the base, essentially the area of this face, and multiply it by its extension, that is to say its height, we can find the volume. Okay. So how can we find this area of the top portion? We know the area of this whole circle, the area of this whole top portion right here, would be given by pi r squared. They only give us a diameter here. It's 22 centimeters, but we know that diameter, or the radius, is half of a diameter. So in this case, r would be equal to 11. So if we wanted to find the whole area, the area of this whole top portion, we could use the area of a circle, pi r squared, and we could say pi times 11 squared. And that would give us the area of this circular portion right here, this whole top of this cake. But we don't want the whole cake, we just want one piece. She cuts it into 16 pieces, so what we can do is we can divide that by 16. And that's going to give us the area of this top portion right here. So if the volume, just going back here, volume is given by base times area of base times height, or extension. Here is the area of the base. What we want to do is we want to multiply it by its extension, or its height of 10. So how much space does this thing take up? Well, let's find its footprint and then multiply by its height. That's essentially what we're doing here. 1/16 of pi r squared multiplied by the height of 10. I think we're good. That's the volume of our piece of cake, of one cake. Let's go ahead and end solve. So we have pi r squared, but only 1/16 of that. We're going to multiply by 10. And this is the volume of one piece of cake. 237.583 cubic centimeters. So writing that out, 237.583 to 3 sig figs, 238 cubic centimeters. All right. Let's go on. Paper is wrapped around all 3 vertical sides of a piece of cake. Find the area of the paper used to wrap around one piece of cake, given that the paper fits exactly. Okay. So here's our piece once again. Vertical sides means, well, ones that extend from the base and go up. So we're talking about this face, this other face on the other side we can't see, and then this face right here. Okay, so we have 2 identical or congruent faces, this one and the one on the other side. What are its dimensions? Well, we know the height of this piece of cake is 10. So we know this, if we're talking about just this rectangular face right here. I'm going to draw it. Actually, that was okay. So here's our rectangular face. The height is equal to 10. And what about this point, the distance from the center to the edge? Well, that's the radius, and it's equal to 11. So we know these rectangular faces. We can call this AR. So we have 2 AR, or 2 rectangular faces. So if we want to find the area of the paper, I hope it's all right if I write AP, area of the paper, it's equal to 2 times AR for these rectangular faces, or 2 times 10 times 11. I'm going to rewrite that 2 times 10 times 11. So these 2 faces. More challenging is going to be this curved face right here. Okay, so what can we do? Let's use that same principle where we're going to multiply by, again, the height, but also we're going to need to find, it's not a flat surface, it's a curved surface. So what is the curved surface of a circle? Well, that's our circumference. So let's find this portion of this circle right here, this edge, essentially. this part right here. Circumference of a circle is given by 2 pi r. In this case, we don't have a whole circumference. We only have 1/16. So in this case, if we're talking about 2 pi r, radius once again being 11, in this case, we only want 1/16 of that. That would correspond to this fractional part of our circle. So let's go ahead and look at this curved surface. This is once again going to be 10, and this right here, this is that curved surface, and that's given by this value right here, this 2 pi r over 16. So right, I'm not sure if this will fit somewhat. That's this portion right here. So we've got these rectangular faces, 2 of them, 10 by 11. Now we also have this curved face. We only have one of those. 2 pi times 11 over 16. So 2 pi r over 16. And then what do we want to do with that? In the same way that we multiplied base times height to find this area, to find this, we've got our curved surface, and we're going to multiply it by this extension. And we're going to get this whole surface. So 2 pi times 11 over 16, multiply by 10 once again. And this will give us the area of paper. So going to the calculator. Here we go. 2 times 10 times 11 plus 2 pi times 11 over 16 times 10. Total amount of paper used is 263.197 square centimeters. Let's write that out. 263.197 to 3 sig figs, 263 centimeters squared. Question 12. The amount of radioactive material present in a sample in micrograms can be modeled by f of t equals ab to the t for t is greater than or equal to 0, where t represents the number of days since the sample was taken. Paula takes 2 samples of this material, sample X and sample Y. The initial amount of radioactive material in sample X is 100 micrograms, and after 138 days, the amount of radioactive material present is 50 micrograms. Part A. For sample X, we are asked to write down A and then find B, given that B is greater than 0. Okay, so here looking at this original equation, we have 2 unknowns essentially. T is the variable that we substitute for time, number of days since the sample was taken, but A, B are going to be constants that we're going to need to find out. So here we have 2 unknowns. In these situations, when we're trying to find the unknowns, especially for these functions, exponential functions, we are often want to make use of some initial parameters that they've given us. So here, our function is in terms of f, amount of radioactive material, and t. And we actually have a few coordinate points here. The initial amount, that's when t is equal to 0. When t is equal to 0, f of 0, or that initial amount, is equal to 100. That's kind of a coordinate point, actually. We could represent it as 0, 100, and then substitute those values for f and t. Same, they give us this other value right here after 138 days. That is to say, when t is equal to 138, f of 138, that is to say the output, is equal to 50. And with both of these values, we can substitute and then find our unknowns. So A is going to be the easiest one to start with because t is equal to 0. And we'll see what that does when t is equal to 0. So here's our function. f of t equals ab to the t. Now let's substitute these values of t is equal to 0 and then the output of 100. So output is equal to 100, amount of radioactive material, and a, b, and then t is equal to 0 at that time. So what happens when any exponent is equal to 0, or we raise anything to the power of 0? What happens is this goes to 1. So essentially now we have 100 equals a times 1, and a times 1 is just a, and that leaves us with the equation a is equal to 100. You can write it like that as well. So write down a is equal to 100. All right, so now we know one of these two unknowns. We can substitute that in, and then we'll be left with just this value of b. So I'm going to clear up some space. Maybe I'll move this over here for now. And then let's write out our function with the new piece of information that we found. So once again, we have f of t equals a times, we found a, so it's 100 times b to the t. This is our only unknown right now. We do know that after 138 days, amount of radioactive material is 50, input is 138, output is 150. That's going to leave us with just this one unknown of b that we can solve for. So output of 50 when t is equal to 138. We can solve this with logarithms, but I think it's going to be easier to use nsolve. So let's go to the calculator and do that. So menu, algebra, numerical solve. 50 equals 100 times b raised to the power of 138. That's calculated to solve for b. Okay. So b is equal to 0.99499, or to 3 sig figs, 0.995. Let's go and write that out. B is equal to 0.995. And I guess we could write that out here as well. Okay. Let's continue on. After 30 days, there were 4 micrograms of the radioactive material present in sample Y. Use your value of B found in part 2A to find the initial amount of radioactive material in sample Y. Okay. So, initial amount, that's an interesting question. So, if we look at this function right here, this is essentially an exponential function. F of t is equal to a times b to the t. B represents the decay constant, so we're multiplying by b t number of times, and then a represents our initial amount. This might actually look a little similar to this function right here. So un is equal to u1 times r, and then for our geometric sequence we have this n minus 1. We're multiplying it by, well, n minus 1. That's just because we start at the first term, second term, third term for geometric sequence, whereas in a case like this, we can have t is equal to 0. But I guess the idea behind this that I'd kind of like to show is that when we're talking about our geometric sequence, what is u1? u1 is that initial amount. And what is this r? This r is our common ratio, what we multiply by to go from one term to the next. So these have a similar structure, and we can kind of use this to say, okay, if they're asking us to find the initial amount of radioactive material, well, they're asking us to find A. We know what B is, so we're again faced with this situation where we know one of these unknowns. We know an input, T is equal to 30. The output, the amount of radioactive material, is 4 micrograms. And now we just need to find that last unknown, in this case, the initial or starting value, which is A. So let's go ahead and do that. So here's our function, f of t is equal to a times b raised to the power of t. We're going to use the value of b that we already found. We found b was equal to 0.995. Now we have the output, amount of radioactive material, and t, the time. We actually know both of those values. when t is equal to 30, f of 30, or the output when t is equal to 30, is equal to 4. So now let's substitute that and then find that last unknown. Output is equal to 4 when the input is equal to 30. Now once again, we've got one equation, one unknown. We can go ahead and solve. So go into the calculator, menu, algebra, numerical solve, and we'll just put in that information. 5 raised to the power of 30, and we'll ask the calculator to solve for A. Okay. So the amount of radioactive material present initially was 4.649 or 4.65 micrograms. So A, let's write this out. A is equal to 4.64909, or to 3 sig figs, A is equal to 4.65. I think it's always a good idea to put units. Micrograms are actually like this, I believe. Micro, this m is this mu. But if you wanted to, I'm sure you could also write micrograms. All right. Question 13. Soroya is designing a gift box in the shape of a rectangular prism, as shown in the diagram. The length L of the box is 1.5 times the width W of the box. This can be expressed as L equals 1.5 W. The height H of the box is also labeled on the diagram. The box has a volume of 10,000 cubic centimeters. Soroya wants to minimize the surface area of the box. Find the width of the box. Okay. Interesting question. We're dealing with two concepts. We're dealing, actually, potentially three. We have surface area. They've given us the volume here, so that is, by and large, something that we're going to need to make use of. And since we're talking about minimizing, potentially we're going to need to use the derivative, use some calculus, or potentially we can actually just graph this and then find the minimum. Okay, so if we want to minimize surface area, it suggests that we're going to need to create an equation for surface area. That is to say, with this rectangular prism, we'll need to add up the surface area, the area of this face, times 2, area of this face, times 2, the one on the other side, and the area of this face, times 2, on the other side. And then we would have some function which relates surface area to potentially actually two variables, length and height. And then I think we'll draw on volume here to find that last unknown. So essentially writing two equations and then being able to reduce or end up with one equation with one unknown, or one function and one unknown, and then minimize. So what does that look like? So let's actually just call this A1. Let's call this A2. So these surface area, these faces, and A3. So if we can call this as the total surface area, maybe I'll write it here. Surface area, area total. Let's go area total actually. AT, area total, is going to be, well, 2 times A1, of course, because it's 1 on each side. They're symmetrical faces. Plus 2 times A2. And then lastly, 2 times A3. So now if we can create an equation for the surface area, this is what we essentially want to minimize. There's one other point. We're going to need to use this information here. They've told us that L is equal to 1.5 W. That means we can express L in terms of W. And that's going to be important. I just want to write it out here. L is equal to 1.5 W. Because when we create an equation, 2 times A1 plus 2 times A2 plus 2 times A3 and so on, we want to minimize the total number of variables. In the end, we want to create an equation, surface area in terms of just one variable, because then we're going to be able to minimize, that function. So we can either just work with L and then substitute 1.5 W, Actually, let's do that. I think that's going to be the most clear way to show exactly what we're doing. All right. So let's add up each of these faces. Start with A1. A1, this is a rectangular face, so it's length times width, or in this case, L times H. So 2 times, and then we'll have L times, all right, times H, plus 2 times, and then if we're looking at this, this is going to be width times H, W times H, W times H, plus 2 times, and then if we're looking at this top face, this is the length, and this is the width, so it will be L times W. L times W. L times W. Okay, so we actually have an equation, in some sense, for the total surface area right here. But we also have 3 different variables. We have L, H, and W. If we can go ahead and reduce this to just, looks like potentially W or H, then we should be able to write this out with just one variable. So one thing we can do is we can get rid of the L by substituting this 1.5W. Wherever we see an L, we can replace it with 1.5W. Why? Because they know they're equal, or we know they're equal to each other. Remember, the equal sign essentially is, right? L is 1.5W. So wherever we see L, we can replace it with 1.5W. That's what I'm going to do now. I'm going to just, here's an L, here's an L. Need to make a little more space and write this as 1.5W times H. 1.5W times H. And then here we had L times W. So this is going to be 1.5W times W, where this red is. So again, replacing L with 1.5W. 1.5W times W. All right. So now we just have an equation in terms of W and H, and then W once again. Still too many, we just want one variable. So what can we do? We can make use of this volume. They've given us the exact value of this, the volume of this container, or at least the volume that it needs to contain. If we're talking about a rectangular prism, we have area of the base times height. That will give us the amount of space something takes up. So find the area of the base, multiply by height, and that will give us the volume. So I want to write that out. Volume is equal to area of base times height. So in this case, what's the area of the base? It's L times W. So area of the base is length times width times, and then of course, the height. So it's length times width times height, and all of this, should move this over a little, all of this is equal to, all of this is equal to 10,000. So our volume itself is equal to 10,000. Now we might think that this actually doesn't help us too much, but remember we can substitute L for 1.5W. So we can actually reduce this as well. So 10,000 equals 1.5W times W times H. 10,000 equals 1.5, just cleaning this up a little, W squared H. Okay, now you might think, hey, how does this help us? But what we have here is 2 equations with 2 unknowns. We have 10,000 equals 1.5 W squared H, and then this surface area function in terms of W and H. And we might say, oh, if only we could write this all in terms of W. The question is, how can we get rid of the H? In the same way that we got rid of the L, that is to say, setting an equation, setting H equal to something. If H is something in terms of W, wherever we see that H, we should be able to substitute and get rid of it, write it out in terms of W. So here is where it might get a little, I don't know if I would say complicated, but we're going to need to draw on our algebra skills. How can we get h all by itself? Right now it's being multiplied by 1.5 w squared. So what's the opposite of multiplication? The opposite of multiplication is division. So let's go ahead and divide both sides by 1.5 w squared. 1.5 w squared. When we do that, 1.5 divided by 1.5 is just 1. 1 over 1 cancels out. And w squared over w squared cancels out as well. So now we have h is equal to 10,000 over 1.5 w squared. Once again, this equals we can kind of think of as an is. So what is h? H is 10,000 over 1.5 w squared. That means wherever we see an h, we can substitute it for this 10,000 over 1.5 w squared, this expression right here. I'm not sure there's going to be enough space, but I think I'm actually going to need to move this down if I can. So let's take this. I think we're going to need a little more space to work on this. And this, of course, is going to be useful for us as well. All right, let's go ahead and reduce this thing. Right now it's in terms of w and h. We know what h is. It's this business right here. Wherever we see an h, let's substitute it out for this, and then we can get an expression all in terms of w, and that's what we want to minimize. So let's go ahead and do that. At is equal to 2 times 1.5w, that can stay. And then h. What is h? H is equal to, hope this is okay to include these double brackets like that. I mean, in terms of not introducing too much kind of complexity and so. All right, let's use square brackets just to help draw a distinction. Might look a little funny, to be honest. 2 times w times h. Don't really want that w, or sorry, don't really want that h. So w times h. H, once again, is that 10,000 over 1.5 w squared. And then lastly here we had 2 times 1.5 w times w is just w squared. Okay, it might look a little funny, but there it is. We've done it. We've written our surface area all in terms of w. And now we want to find exactly this. We want to find the width of the box. So here's some function. We put in different values of w. What is the value for w that is going to give us the lowest surface area? So I think in this case, we can actually clean it up a little, but we can also just go ahead and graph this as it is. If we want to clean this up, we see w being divided by w squared. We could cancel this square and then cross out this w, but our calculator should be able to handle all of this. So let's go and put it in just as it is. So let's go to the calculator here, and let's go to our graphing feature. And we have 2 times, we're going to need to write this in terms of x. 2 times 1.5x, open another bracket. 10,000 over 1.5x squared plus 2 times x, open up another bracket, sorry, a fraction rather, 1.5x squared. I think we need a plus here actually, there we go. 2 times 1.5x, 10,000, 1.5x squared, 2 times x, 1.5x squared. This looks good so far. And then lastly, plus 2 times 1.5x squared. All right, cannot accept invalid input. So is there a place where we have, this looks okay to me, unless I've thrown in a W somewhere. Okay, let's see. 2 times, this is good. No, it is not. Okay, so 2 times this, just making sure that this 2 is being multiplied by everything here. This is good. Plus 2 times W 1000 x squared. This is good. And this is plus 2.5. This looks good now, I'm hoping. Cannot accept change. I'll try one more thing. 2 times 1.5 W. Could it be because of this x divided by x squared? Let's see. 10,000 wx squared. It looks good to me. I'm going to simplify. Maybe that's what it's complaining about. Let's see if that helps. Ah, it did. That's strange. So in this case, we actually did need to simplify before the graphing function would accept our input. So let's see if ZoomFit will provide us an image of this function. Okay, not bad. Okay, so it looks like a kind of rational function. We are only concerned with this positive domain right here because, well, the width dimension can't be negative. Looks like it reaches some minimum and then it's going to increase again. So it should start increasing. I'm going to change the window. I'm going to put a larger value. Right now it's only going up to 15. Let's get a larger maximum value for x. Let's put it to maybe 115. See if it starts to increase once again. And it does. So it goes down, reaches some minimum, and then it starts to increase. If we want to see this a little more, I think we already have our minimum, but this is actually a very large number. So what can we do? Let's just say negative 1,000 and positive 1,000. I think this should still be good for us. No. Okay, this times 10 to the 6 is quite large. I'm actually going to forgo this idea of adjusting the window for now and just find the minimum. So let's find the minimum here. There it is. So our function reaches a minimum at 17.7. So when x is equal to 17.7, our function, our surface area has a area of 2,823. Guess we can adjust this window now if we want to. Let's put minimum at maybe negative 10, just so we have the bottom. And then we'll put this at maybe 5,000. That should give us a nice kind of display of the minimum. So there it is. That's our minimum point once again. So when the width is equal to 17.7, our surface area is equal to 2,823 centimeters squared. Let's go back and write that out. So W equals 17.71 or 17.7 centimeters squared. 5-mark question. I would say it's probably a good idea to draw a sketch just to make sure you have your process marks. And we can just draw something like this. That's a little too steep, I think. Something like this. And then label our coordinate point, 17.7. And then the surface area itself was 2823. Or if we wanted to, 2820 to 3 sig figs, 2823. Okay. Nice question. Maybe we'll do a little recap just really quick. Originally, they gave us this question where they're asking us to minimize the overall surface area. They also gave us this volume. IB doesn't usually give you something that you won't need to use. So chances are we would need to create an equation with volume. When we started creating an equation for surface area by adding up each of these faces, 2 times A1, 2 times A2, 2 times A3, we saw that we had an equation in terms of L, W, and H. They also gave us this relationship between L and W. So that allowed us to, whenever we saw an L, we could replace it with 1.5 W. And with that, we had an equation just in terms of W and H. Still, it was too much. We wanted, in the end, to have an equation just in terms of one variable, ideally in terms of width. So what could we do? Well, we could make use of this volume equation. That is to say, length times width times height was equal to 10,000. Putting our variables in again, we could switch out L with 1.5 W, and then lastly, we'd had an equation in terms of W and H. Getting H all by itself, we were then able to substitute out this H and get this just in terms of W. Now we've got a surface area equation just in terms of W, graph it, find its minimum, and then that's where we have the minimum surface area. We also could have worked this out by taking the derivative. That wouldn't have been too bad either, but graphing works just as well. Okay. All right, so that's the end of this exam. As always, I hope it was helpful, and best of luck. Take care.